numerically as well as analytically. We have solved several examples, and then now we are moving on to the two-dimensional finite element. So from today's class, 2D and 3D FEM will be taught. Okay. So what we'll do is we'll just again revisit little bit older stuff, and then come back and to the 2D things. So first, what I will start is with the Lagrange functions. So let us talk about first continuity. So if a variable phi of x is continuous, it is C0. If d phi by dx is also continuous, then it is C1 and so forth. Okay. So when we are kind of uh, doing a beam problem, we show that we need a C1 continuity. So for example, if we had a bar example where d by dx ae du by dx plus some p is equals to 0, when we solved it, the requirement for the u has to belong to C2, because not only du by dx but also has to be continuous, that is same as u. But if we are an approximation u tilde, we just showed that we can still get you a solution when u tilde just belongs to C1. That was our thing in the one dimensional stuff. Similarly, in a one dimensional beam kind of a structure, here W has to belong to C4. But we got an approximation where W tilde is just C2. So all these stuff were with respect to one dimensional state, and based on these things we have come up with, in this case we have developed something called as Lagrange shape functions by saying that u tilde is equals to ui ni, whereas in here w or y, whatever you want to call it as, is equals to wi Lagrange functions, shape functions, and where si are Hermite. The difference between the both the thing is, here your degree of freedom is only u, whereas here degree of freedom is both w and dw by dx. So it has multiplicity more, one more multiplicity at the Lagrange shape functions but Hermite functions. And we also have shown little bit the same thing in the two-dimensional state in the previous thing. So but still let me just repeat it. So anyway, let us talk about the characteristics of the shape functions. So let us say C0 shape functions. Okay. So that means if you have shape functions which are ni, so then your uh, so let's say, since if I take phi is equals to phi ni, that means both phi of x and all n of x, ni of x are of same polynomials. Okay. Further, for any shape functions, what we said was ni of x I is equals to 1 and ni of xj is equals to 0, where xj is not equals to xi. And further, the last one, which says that C0 shape functions, is it should represent, this should also represent the rigid body motion. That is the important thing of C0. That means any rigid body which is constant has to be represented by Pi Ni, and since all the things is also C, then the summation of Ni would equal to 1. So that is the characteristics of C0 shape functions. Now let us do the same thing in terms of two-dimensional things. So when we come to the two-dimensional shape functions, let us take a simple element which is these two sides are parallel to x and these two are parallel to y for simplicity. So let's this distance be b, this distance be b, this distance be a, this distance be k. So in that case, our coordinates, and let's 0, 0 be this part. That means this is a, b. This is minus a, minus b. This is plus b. This is minus a, minus b. This is a minus b. So then I will take my variable which has to be interpolated, phi x comma y, as since I have 4 nodes, which is node 1, node 2, node 3, node 4. So I can have at most 4 constant in my polynomial. So this is a0 plus a1x plus a2y plus a3xy. Anyway, I have already proved it since I have these shape functions, but I'll redo it for the benefit of the crowd. So we want to write this as phi ni. It runs from 1 to 4 because there are 4 nodes. So this thing I can represent it as 1 x y x y times a0 a1 a2 and A3. So that means this can be further written as x times A, as this is where so what we'll do is we'll take this expression, which is equation 1, and substitute A comma B here. But we know that this is nothing but V1, and that will equals to 1 A B A B. I'm using this expression times this is different A's. This is a different A. This is, that's the reason I put an underscore A. That means it's a vector A. Similarly, V2 is equals to 1. Sorry, this is the coordinates of. Let me just. I made a small thing. So the node 1 coordinates are not A comma B. The node 1 coordinates is minus A minus B. So let me just correct it. So this is minus A minus B. This is correct. So this node 2 is A minus B minus AB, and V3 is 1 A B AB, and this is V A comma minus V. This is V A comma B. V4 is equals to V minus A comma B. So I can write this thing as V1, V2, V3, 4 is equals to 1 minus A minus B AB, 1 A minus B minus AB, 1 A B AB, 1 minus A B minus AB times. So this thing I can further write it as, which is phi, which we have just called it earlier, this I call it as capital A times small a. Now if I want to work out for this value, then I know that A vector is equals to capital A matrix inverse times phi. Now I take this thing and substitute in the equation 1, which is here, right? So that means my phi x comma y, which is nothing but x times A, I can write it as x times A inverse times A. But we know that this is sorry times phi. But we know that this is also equals to n into p. So that means our n must be this one together, right? So I think this I have repeated just for the benefit of the students. So the shape function n is in general obtained as the basis vector times A inverse. Okay, since this we have already developed it, I'm just giving it for your references. So now one can develop this shape functions appropriately. So for our case, so functions. So let's say our um, x vector. So since A B x, so our capital X, sorry, this is two dimensional, so I have to give y also, is equals to 1 x y and star y. Further, and our A matrix is equals to 1 minus A minus B times AB and 1 A minus B minus A star B, 1 A B A star B, 1 A minus A minus B minus A. And our n is inverse of A star x. Okay, let's inverse is inverse. So Okay, let us simplify it. So that would be so size of n n comma 1 is this, n comma 2 is the other one, n comma 3 n and so anyway, let us check my program once if I have made any problem. So this is, so this would be minus AB. So let us rerun it. Let us just check once before I move on. It's 1 minus CA minus BAB. 1A minus B minus AB. 1AB, AB, 1 minus A, B minus A minus B. So now let me run once more. So now it has come correctly. So what is N1? N1 is given by N2 is A plus X for AB. N3 is A plus X B plus Y by 4AB, and these are our shape functions. So this is how we have developed, and the same thing can be used for different set of the shape functions. So then I mean, I will leave it to you to try it out for the other things. If you have any simple, I mean, you can do this thing with with the bare hands. You don't need a MATLAB. Complicated things, you can still go for these kind of generic things. So these are the shape functions. Now let's come back to certain things what we have again done. So we obtain the shape functions. When we are obtaining the shape functions, the important crucial part for selecting the approximation P is the basis. Why did I choose this basis? For that, let me recall, which I have already said. You try to invoke Pascal's triangle. Okay, so So now if you have a square, blindly people can this as the 4-noded quad. Okay, if you want a 9-noded, I would say you put this as your, this is 9-noded, this is 4-noded. Now I have already repeated this. Next, in case if it's a 3-noded triangle, I would prefer you to take this one, which is 3-noded triangle. And if I want to have 6-noded, then this is 6-noded triangle. So the choice of capital X is from the Pascal's triangle for a reason. The reason is, see, these quantities are nothing but our approximations. In fact, you can call it as p tildes. So the actual function p you never know. We are kind of only approximating it using some polynomial. So in the polynomial basis, what happens is, if let's say, if I will show it again for a one-dimensional state, so left t is your exact and t tilde h to the power of p. So here what happens is, if t tilde is selected as, let's say, the choice of t, choice 1 is a naught plus a1x plus a2x square, let be the first choice for a 3-noded triangle. Let's, so three-noded, let's say it's the same thing for choice 2. If I take it as a naught x to the power of 5 plus a1x plus a3 x3. So what happens is, in the basis is nothing 1 x square. The basis in this is x cube. I mean, you can choose it, you can rewrite it in any. So take the complete polynomial basis up to infinity, that is the complete polynomial basis would be 1 x square x cube, so on, x to the power of capital N, and capital N tends to infinity. Now from that, from this, let's say you call it as universal set. From universal set, you remove x and then check the least power of the difference set. That will be the power p. The p is the least power of the difference between u minus x. In this case, the power would be, in this case, p is 3, whereas in this case, p is equals to 0. That means, even if I, let's say now, if I have a mesh size of h, and if I increase this mesh or decrease the mesh by half, okay, then according to that, my error would be h to the power of, error is h to the power of p. So this would be h to the power of h by 2 to the power of, let's, p is 3 here, So this is h by 2 to the power of 3, that is error decreases as 1/8 compared to the error of the this one. So mesh size 1/2 decrease will result in error diminishing by 1/8. See, you want error is like an enemy in numerical procedure. You want enemy as high as possible, then error would diminish. In order this p to be as high as possible, this guy has to pick all the lower order things so that the lower one will not go to this guy. Here we forgot to remove take 1 here. That's the reason p to the power of 0, which is nothing x to the power of 0, that is p is 0, is remaining with this guy. And that's the reason in the second case, this is for the choice 1. For choice 2, since h to the power of 0, that means your error doesn't decrease. By taking such kind of thing, your error remains as it is, h to the power of 0, so 1. But you cannot characterize it with the decrease in however small you do 1/2 of the mesh, it will not decrease. You do 1/3 of the mesh, it will not decrease. You do 1/4 of the mesh, it will not decrease. Whereas in this case, if I do 1/3, then to the power of 3, the error would decrease as 1/27. If I do 1/4 as 3, then error would diminish as 1/64. Whereas in this case, for all the cases, the error would remain same. So you will be thinking that I have did every formulation exactly the same, but your choice of basis is so bad that it will result in no mesh convergence, or with respect to by increasing the number of elements, you would never see the error being diminishing because you gave the lower powers to that. So in order to avoid that, we come up with choosing the basis through Pascal's triangle. If you choose it in this manner, in the shown form, so it is guaranteed that the lower order powers will be retained with our approximation, and higher order power will be left out with that. Anyway, based on that, you can determine what is P, and once P is known, then you know that if P is the highest power, then you know that the H convergence will always lead to a better result. So your approximation is much better. So it's not only the same amount of work, sometimes you have to choose your approximation in a proper manner, otherwise you end up in a so kind of work which will not yield any beneficial results. So with this as a background and the shape functions, that is the one thing which we have dealt with. The same thing applies for the two-dimensional case. So in the two-dimensional case for P, which is x comma y, it also depends upon the power of x as well as the power of P. So your universal set has two parts, one coming from the x part and another coming from the y part. So your so let me do it with respect to u. If u is an exact function and u tilde is an approximation, then it h to the power of p is also there, where this p is the minimum power based on x as well as based on y, very similar to what you have done in the first part. Okay, so the same things applied when you do it in the multitude of dimensions, but the things will look little bit different and more complicated. So this is the first one more important stuff, which is this will tell you the convergence. Okay, so for convergence, what you have to do is, for better convergence, so you choose complete polynomial. The complete polynomial is a polynomial where all the lower terms remain with the approximation and higher powers remain with the error. So that is for convergence, this is one criteria. Okay, and this is not the only thing. So this will tell you that it will converge very quickly. And anyway, this error, whatever you have, can be characterized as c into h to the power of p. This will give you order of convergence and this will give you the rate of. So what we are doing is, by choosing a complete polynomial, we are choosing this. Based on different things, we can also show that, but we can also, if we lower this quantity also, we can. This term is a crucial thing, which is our error. Okay, so anyway, these two parts are there. This is especially important in every part, 1D, 2D, and all the things. But there are other things that come into the part in the two-dimensional state is compatibility. So this we never discussed, not discussed in 1D, because there is no such problem as compatibility in 1D. But when you go for multitude, these kind of new things will creep up. For example, what is compatibility? Let's say you and your friend wants to go to a movie. So if you say, I want to go for a comedy movie, and your friend says, I want to go to the horror movie, then what happens is, unless you resolve the things, that means you both are not compatible to which movie you want to go and watch. Unless both agree on to it, there will be a fight. So maybe God knows that you both fight and you don't end up watching a movie. So that means it's a bad thing, right? So same thing can happen even in our finite element simulations. But in 1D, why doesn't it happen is, let's say have several nodes that are present and elements that are present. Let's say I take this as element 1, this as element 2, this as element 3, this as element 4. Okay, or whatever it is, any order is there. Let us pick some element and let's see. This is U1, U2, U3, U4, U5, because the nodes are 1, 2, 3, 4, 5. But we know that when we are solving the finite element, no matter I come from this polynomial, for this one u approximation for the element 2 is given as u2 n1 plus u3 n2, right? Because these are, I mean, okay, let me rewrite it as, for the element is degree of freedom 1 n1 plus d2 n2. But what is the degree of freedom at this node? This node is, for the element 2, it is the degree of freedom is nothing but u2. The degree of freedom at this place is u3. So this I can write it as u2 n1 plus u3 n2 is your approximation. That means how the displacement in the second third. So this is u2, this is u3. It can be some linear function because I have only two nodes. That means at most I can fit a linear curve. So this is u2, this is u3. Now if I take the next element, which is element, if I take element 3, which is 3 and 4, here I can again write my approximation for the thing. Same thing I need to do is d1 n1 plus d2 n2. The shape functions may be same if the length is same, but what happens is your then the degree of freedom at this place is u3 and this one is u4. So u tilde of 3 is u3 n1 plus u4 n2. So now what I want to do is, I want to evaluate this at node 3. So if I evaluate at the node 3 through the element 2, since that is U2 evaluated at length at node 3 and U3, I know that this is 0 by the characteristic of things and this is equals to 1. So this is equals to U3. Now if I want to evaluate this thing at 0, because x is measured from here in this case and the x is measured is, it will give, this is U tilde of 2 has given thing as the displacement, sorry, at L. So U tilde of 2 at L and U tilde at 0 is U3 N10 plus U4 N20, but I know this is 0 and this is 1, so this is U3. So the polynomial for this element is giving U3, this element is also giving U3, and at node, why? Because at nodes they have to, and at nodes the finite element has to exactly agree, and this element and that element have a common boundary which is nothing but node 3. The boundary between node 3 is the boundary between element 2 and element 3. So this is the boundary. The node itself is the boundary, but at the node this is exactly is obtained no matter you are coming from this polynomial or you are coming from this polynomial. However, this will not stand true for the higher order elements or higher dimensional element. This may not be satisfied always higher dimensional element. And if it doesn't satisfy, then it is called non-compatible. So let us see how is the non-compatibility by looking at it at a greater depth. So let us take two elements. Okay, so let's take two elements such that this is element 1 and element 2. Okay, this is one choice. There is another choice. This is straight line. I might not be drawing as a straight, but consider it as a straight line. Element 1, element 2. Another choice is this is choice 1, choice 2, and choice 3. So this choice 1, I'll do it later because that will give us the thing, but let's focus on these things by taking an approximation. U tilde is equals to A0 plus A1x plus A1y plus this is A2y and this is A3xy. That means I have taken 1xy xy into A. This is complete. I have still, I'm not saying the polynomial is not complete. It is still complete, but it may not be compatible. That will come to know depending upon the choice of the elements. So let me come to that. So anyway, let's see. This is our approximation. What is the equation of this line? So like this. So this is for the element 1. Similarly, for the element 2, you will have b naught plus b1x plus b2y plus b3xy. Okay, so this is also complete for element 1 and element 2. We don't know what are the coefficients of a naught, a1, a2, a3, b naught, b1, b2, b3, but okay, let us see what is the equation of this line. So this equation of this line is x is equals to constant, because it is an axis parallel to, sorry, it's a line parallel to y axis. So that means it has to be x is equals to constant. And so let me put it in this equation. Okay, in this equation. So that means u tilde in the line, let's call it as line L. So u tilde along the line L is equals to a naught plus, since x is equals to constant, I will write it as, I can write this one as a naught with new coefficients. I can write it in whatever manner, because this is a constant, this is a constant, this is also a constant. So all together I can write it as a special constant called capital A naught, and this is a constant, these two are again a constant, this is a constant, and adding up all these things I can write it as a1y. Similarly, I substitute u tilde along the element thing from the second element. So there is some interpolation function here. From this I'm estimating what is the value along this line. Okay, so that would say that this would be b naught plus b1y. Now how many values I know along this line? I know exactly the value at this node, and I know the value at this node, and I need to fit a curve between these two. If you know two values exactly, if you want to fit a unique thing, the only unique curve with knowing two values is a polynomial with, if there are n points are known, values are known, then you can fit uniquely a polynomial of unique minus 1 can be fit. That means either I do it, let's say we both are sharing the boundary, let me call it myself as element 1, and we are estimating the value of the field variable along the line L. I am coming up with this as a equation, this as equation. I know the two values, so we both has to get the same equation. It has to be that a naught is equals to b naught and a1 is equals to b1, because we know 2-point values. And we can do it uniquely, because no matter I solve it or you solve it, because it's a linear equation, in terms of y we'll get the same thing. Similarly, in the same manner, if I solve this along this line L, I can show that for choice, this is for choice 2. So similarly, for choice 3, u tilde of element 1 along the line will be sometimes something a naught times, this is, let me call these are different a naughts compared to the previous a naughts, and along the element 2, along this for the element 2 along the line L is some b naught dash plus b1 dash. And how many point values I know again along this line? I know this value at this place exactly, I know at this place exactly. So if I know 2 points, I can fit a linear curve uniquely. No, that means if I assign it to even 100 people, all 100 people will come up, or 1000 people, or n number of people, all has to come up with the same values or same equation if they are starting with an n minus 1 polynomial. The n minus 1 polynomial, because I have given 2 points, That means I can fit uniquely 2 minus 1 is 1 linear polynomial. That means this guy is also having a linear polynomial, that guy is also having a linear polynomial. That means both the people will end up with the same equation. However, so these two are same. Now, however, let's check for choice 1. So let me take the have a relook at the choice 1. So for the choice 1, let's write the equation of this line. Let's call it as line L. The equation is y is equals to mx plus c. Some y is equals to mx plus c. It cannot be x is equals to constant. It cannot be y is equals to constant because it is not vertical nor it is horizontal. So it cannot be not x is equals to constant, y is equals to constant, but it is a linear equation of this form. Now I take my which is nothing but a naught plus a1 x plus a2 y plus similarly estimation from the element 2 is b naught plus b1 x plus b2 y plus b3 xy. Now wherever y is there, I'll substitute mx plus c. This as mx plus c. This as mx plus c. Same thing as mx plus c, and this one as mx plus c. So if I do that, what I'm getting is u tilde hash 1 along the line L is some a naught plus a1 x plus a2 x square, because this is x into another x would be x square. So at most we have x square, x into another x here. And if I do other combination, I'll get something like this. Similarly, if I do coming from the element 2, I get b naught plus b1 x plus b2 x square. Now, how many values I know along this line? Along this line, I only know the value exactly at this place and this place. So, I know two values, that is n minus 1, sorry, n is equals to 2. Uniquely, I can fit n minus 1, that is 1 degree polynomial exactly. But my degree of polynomial is not 1, it is both the 2. So each may end up with a different polynomial. Maybe in only some fortunate cases both may come up with the things. Otherwise, both the guys, you have family of curves. Even you can only determine only up to two constant, the third constant remains. If the third constant remains, that means you have family of curves. Okay, that means you and that means element 1 and element 2 may not agree on the same thing all along the boundary except at the boundary points. That means since this is quadratic, the element 1 can estimate it something as like this, some quadratic form. It will estimate it as like this from element 1. The second guy something like this, the element 2, because it's a quadratic curve. since it's a quadratic curve, they both agree at this point, but they don't agree in between all along the boundary. It's like, let's say if we both are neighbors, my parents and your parents are very nice to each other. However, me and you will always quarrel, right? It's like a boy and a girl, if they are in the neighborhood, they're sharing the boundary things, they're always cribbing about each other, but each parents can be nice. So this is like a condition that they agree with this parent is agree with this thing, this would agree, but in between guys will not agree with each other. If they are not agreeing with each other, that means one guy is maybe penetrating into the other, or it may create void, which is unphysical. The unphysicalness comes by introducing some numerical forces which are not required, which is nowhere there in the problem. That means this incompatibility is an undesirable result. So incompatibility is an undesirable result. I still took a complete polynomial. The way I took the polynomial is, even though I took a polynomial which is complete, you may not always, maybe if you're lucky, you and your neighbor will always stays. I mean that you will not have any boundary dispute. But even one guy wants to bulldoze the other off, then there is always a problem. That means you have put your parapet wall little bit into my area, and hence this and forth or something like that. Those quarrels will come back again, right? The same thing. So because they are have different functional form, obviously there may be a reason that they would not agree with each other. So and hence this is called incompatibility. So how to make sure that incompatibility is removed? There are several ways you can remove such kind of things. One thing is to make sure that your elements are always sharing a vertical and horizontal boundary, but not always you can guarantee such kind of things. You may have a complicated geometry in which you need an element which looks like something like this. So in those scenarios, there are certain ways to enforce it even for normal formulation exactly. But by default, if you want to do it, you can use something called as isoparametric formulation, or to do it in a natural coordinate system. In natural coordinate system, what happens is this is already ported into a natural coordinate system which looks like a perfect square with horizontal and vertical there and come back to the real world after you do the assembly, then such kind of things can be avoided. That is the most easiest manner. But that is the doing your formulation in the isoparametricness. So that is one way, and there are some adjustment you can to do to get the things right along the boundaries, that will also ensure it. Or uh, just making sure that you have horizontal and vertical boundaries along will also do that, but this is uncontrollable in all the generic scenarios. So it is better to go for the isometric formulation. So later in this, after I have finished this kind of a topic, when I come to the natural coordinate system, I think in the next chapter I will tell you how to deal with the things, same things in an isoparametric formulation. Everything remains same, except first we transform this into another element in an isometric space, and then do the formulation in that part, and rest of the things remains as it is. So for now what we will do is, we understood what is something called as convergence, completeness, compatibility, and convergence. All these two, actually these two will ensure the convergence. Anyway, I generally call it as what is completeness, what is. So these three are triple C is quite an important thing in a finite element method. So with this, so what we have done is, the things that are not there in the one dimensional would come back and hit on to us when we go for the multitude of directions. At this point, I will stop and I'll check if you guys have any questions. In 2D, let us define the stress, okay, and the strain and all other things. So anyway, as you know that 2D slash 3D, so let us define something called as so sigma, which is stress, is given as sigma 1 1, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, and sigma 3 3. Now let's assume this is x, y, and z, or alternatively 1, 2, or 3 directions, whichever is comfortable for you. So this is nothing but sigma is sigma ij ei plus ej. Is the direction of the stress component. So for example, if I have this one, the plane normally is n1, so or e1, n is equals to e1 along one direction, and the component is also this vector is also in the one direction, so this would be sigma 1 1. If I have this thing, this is acting on the still on plane with a normal e1, and it is directing on the direction 2, so it is sigma 1 2 and sigma 1 3. So this can be represented as plane normal, this is direction of the component. So that is how this has been numbered, and for a two-dimensional state of stress, this is nothing but sigma. So for example, I can represent this as using a stress block. This is, let's say this is x and y. The normal for this is E1, is the normal. Normal for this guy is E2. So this component is along the 1. So this is sigma 1 1. So this component is, it is acting on plane with a normal in a direction 2. This one is sigma with the normal 2 and acting in the first direction, and this one is sigma 2 2. sigma, sorry. So this is with a normal 1 and on the direction 2, and this is sigma 2 2, and this is sigma 2 1. So this is the state of the stress. Next, what we'll do is similarly there would be a strain definition. The strain definition would be epsilon would be in the similar manner: epsilon 1 1, epsilon 1 2, epsilon 2 1, epsilon 2 2. Next, the strain epsilon ij, it's again the same. This is plane normal and this is its direction. Further, epsilon ij has a definition. Epsilon ij is equals to 1/2 comma j and u j comma I. That is nothing but, anyway, you might have seen it as 1/2 dou ui by dou xj plus dou uj by dou xi in this manner. For example, if I want to find out epsilon 1 1, according to this definition, it is 1/2 dou u by dou x1 plus dou u 1 by dou x1, that is equals to dou u1 by dou e are the displacements along 1, 2 and 3 direction. That is, in general you used to call it as displacement u, v, w. Now we will further call it as u1, u2, u3 synonymously. Okay, so further epsilon 1 2 is defined as 1/2 dou u1 by dou x2 plus dou u2 by dou x1 is your thing. If you, I think you might have seen this in terms of definition of u and v, which you call it as dou u dou y plus dou y by dou x conventionally, right? So because 1 to 3 are synonymous to x, y and z direction, this you might have seen it. So similarly, epsilon 2 2 is equals to dou u2 by dou x2, epsilon 3 3 is equals to dou u3 by dou x3, and epsilon 2 3 is equals to 1/2 dou u2 by dou x3 plus dou u3 by dou x1, and epsilon 3 1 or 1 3, whichever you want to write it as, is equals to 1/2 dou u 1 by dou x3 plus dou u 3 by dou x1. Now you can see that by definition epsilon ij is equals to 1/2 ui comma j plus uj comma I. If I rewrite these two terms, I can write it as 1/2 uj comma I plus ui comma j, but this is equals to epsilon ji. So by definition, epsilon ij is equals to epsilon ji for this is small strain, because for the for small strain. So epsilon ij is equals to epsilon iji. So epsilon is a symmetric tensor, right? Epsilon as epsilon 1 1, epsilon 1 2, epsilon 1 3, epsilon 2 2, epsilon 2 3, epsilon 3 3. 2 1 is same as 1 2, so I will write it again as 1 2. 1 3 1 is same as 1 3, so again I will write it as 1 3. 2 3 is same as, sorry, 3 2 is same as 2 3, so I'll write it like this. Or people generally write it as epsilon 1 1 1 2 1 3 2 2 notation, right? Now this doesn't say that the stresses are symmetric. Okay, the stresses has something little bit different to deal with it. For example, let us say, let us say that, so we have to satisfy any given structure, two-dimensional structure has to satisfy something called linear momentum balance, also called as force equilibrium, and angular momentum, that is called as momentum equilibrium. So for example, if you had a truss kind of a structure, if you are doing summation f is equals to 0, fx is equals to 0, fi is equals to 0, then this is called force equilibrium. If you do summation m is equals to 0, these are called moment equilibrium. Okay, so let us see for a two-dimensional case. The same thing would apply for a three-dimensional case. So let us take a box and subject it to sigma. Let us subject it to uh, the stresses, which is sigma 1 1, sigma 1 2. So this is 2 1. Now by summation of f equals to 0 along x, we know this force is balanced by that, and this force is balanced by that, by summation fy equals to 0. However, the shear forces just remain like this. The shear forces are these things. Now let's say this is not a ferromagnetic material. That means it doesn't have no body movements. So what is a body movements? The body movements are the movements which and try to bring it closer with the north and north pole. You'll see that it tries to resist it by creating a movement so that the north and south can match. So those kind of polarity would exist, and that will create a bending body movements, just like a body force. But body force, you can always feel the weight is a good example of body force. So like that, body movements are also present in ferromagnetic materials. But unless it is, if it is not a ferromagnetic materials, that means if I take moment about any point, since let's say this is dx and this is also dy, which is equal to dx, then we know that two opposite forces separated by distance would create a moment, and this sigma 21 would create something called as a clockwise movement, and 1 2 sigma 1 2, these two are opposite forces and they are separated by a distance again dx, and there are no body moments present to resist it, it is zero. In that case, no matter whatever is the dx, sigma 21 is equal to sigma 1 2. Okay, the same thing can be proved for 2 3 and other directions. So by generality we can say that sigma ij is equals to sigma ji for materials with no body moment, just by the definition of, just by the satisfaction of angular momentum balance. So if it has to, I mean, every structure for equilibrium, not only it has to satisfy equilibrium, if there are no body moments present in it, then the stress is always symmetric. So if you consider stress as symmetric with no body moments, you don't have to explicitly solve your angular momentum balance, and that makes you to only solve for the linear momentum balance for the equilibrium conditions. So for all the generic materials, whatever we see, we solve for non-ferromagnetic. So what we'll do is, we'll consider stress asymmetric in the rest of the course. So sigma tilde is also like sigma 1 1, sigma 1 2, sigma 2 2. Okay, so this is your stress state. Now, so now we had strain relationship with displacement. We had uh, your displacement. I will also bring stress strain relationship in a later slide, but let us see this relationship with the displacement in a greater detail, which is nothing but epsilon ij is equals to 1 half u I comma j plus u j comma I, with a greater look for a two-dimensional state for the finite element sense. So let us take our u1 as a function of x comma y, which is an approximation, which is not exact. So it's, I will try to write it in this manner: u1 tilde x1 and x2 is the displacement along x1 direction, and u2 tilde x1 x2 is the displacement along x2 direction. Now, since we have seen that phi tilde is equals to phi ni, and by the same argument we can do it for u1. Sometimes I call it as u, and this one as v. So let us do it in terms of u as a function of x and y, and this as v as a function of x and y. So that would be better choice of notations. So our u tilde can be written as ui ni, and v tilde is written as vi n. For example, let this be a node 1, this be the node 2, this be the node 3, and this be the node 4. And let me take the regular element. So let me take as a proper regular element, so that which we have already have shape functions with to start. So let me take this kind of an element. We have got our shape functions today, so we have written for a b and 3. Sorry, this is not x and y. I'm sorry about that. B plus y by 4ab. So if I take this as an example, so my u tilde is nothing but u1 n1 plus u2 n2 plus u3 n3 plus u4 n4. Similarly, my v tilde can be written as v1 n1 plus v2 n2 plus v3 n3 plus. Okay, now let us take the definition of the strain 1 1. Epsilon 1 1 can be written as dou u by dou x. That is nothing but dou by dou x of ui ni. That is results in u1 dou n 1 by dou x plus u2 dou n2 by dou x plus u3 dou n3 by dou x plus u4 dou n4. This is our epsilon 1 1. Similarly, epsilon 2 2 is equals to dou v by dou x, sorry, dou y, that is equals to dou by dou y vi ni. That is nothing but v1 dou n1 by dou y plus u2 dou n2 by dou y plus u, sorry, this is not, this is v2 dou n2 by dou y plus v3 dou n3 by dou y plus v4 dou n4 by dou y. Now, since I'm only doing 2D formulation, I'll restrict myself to epsilon 1 to alone. So is equals to 1/2 of dou u by dou y plus dou v by dou x. That can be written as 1/2 of u I dou by dou by dou. So let me rewrite it. So 1/2 dou by dou y of ui ni plus dou by dou x vi ni. So that can be written as, I will take 1/2 common, u1 dou n1 by dou y plus v1 dou n1 by dou x plus u2 dou n2 by dou y plus v2 dou n2 by dou x plus u3 dou n3 by dou y plus v3 dou n3 by dou x plus u4 dou n4 by dou y plus v4 dou n4 by dou x. So now looking at all the equations, one and this as equation 3, I can write epsilon 1 1, epsilon 2 2, epsilon 1 2 as dou n1 by dou x 0, dou n2 by dou x 0, dou n3 by dou x 0, dou n4 by dou x 0, 0, dou n1 by dou y 0, dou y 0, dou n3 by dou y 0, and dou n4 by dou y, and 1/2 dou n1 dou y 1/2 dou n1 dou x 1/2 dou n1 2 dou x 1/2 dou n3 dou y 1/2 dou n3 dou x 1/2 dou n4 dou y 1/2 dou n4 dou x times u1 v1 u2 v2 u3 v3 u4 v4. Now if you look at it, if I take this one, this times u1, anyway second is 0, dou n2 by dou x times u2, next one is 0, dou n3 by dou, and next one is 0, dou n4 u4 is nothing but your equation 1 for the epsilon 1 1. Similarly for the equation 2 is this thing, and epsilon 1 2 is the equation for the third equation is for the epsilon 1 2. So what we have done, these are not exact things, these are approximations. So I can call my epsilon tilde is equals to some matrix called capital B times your U matrix, where U is degrees of freedom. The degrees of freedom for this element is, let us see the degrees of freedom. This is, let us write the nodes first. So this is node 1, node 2, node 3, node 4. The displacements are for this fellow is u1 v1, u2 v2, u3 v3, u4 v4. So the degrees of freedom would be d1, d2, d3, d4, d5, d6, d7, d8. So there are 8 degrees of freedom for this. So, and this guy is a degree of freedom. So some people write it as U, some people write it as capital D. So this is nothing but the degrees of freedom, and this is your strain. So this is your strain approximation, and this is your degree of freedom at nodes, and this matrix B is the thing that connects between the strain and the degrees of displacement matrix. Okay, so the strain displacement matrix is the one that connects between the strain approximation and the degrees of freedom. So with this, what we'll do, we will close today's session and we'll presume on the tomorrow's session with a further stress strain relationships and others, and we'll go ahead use the principle of virtual work to derive the FE formulation for the 2D structures. So with this, if you have any questions, I will be happy to answer this.